away from the surface? Is it pointing into it? And so what you could do, one of the easiest ways to check is go ahead and compute the cross product and then see what's going on at a particular point. And with a sphere, you can readily tell is the vector pointing away from it or into it. So any questions about that one? So if you want to work with the inward orientation, you would just consistently use r phi cross r theta, and anywhere in the sphere, it'll give you the inward unit normal. All right. Now, there's one example involving a closed surface. At least want to start. Suppose we have your friend from the second exam, a tetrahedron. But not the same tetrahedron. X, Y, Z. With vertices 0, 0, 0, 0, 0, 1, 1, 0, 0, and 0, 1, 0. And you want to compute the surface integral of a vector field over this tetrahedron. So I should mention, so we use the outward unit normal, and another term for that that I'll use from time to time is positive orientation. So it's just like with curves. Any of the normal vector to a curve, a closed curve, positive orientation is when the normal is pointing out. So we have the same thing going on here. All right. So what you would need to do to integrate a given vector field over this tetrahedron, well, the tetrahedron has 4 sides. You have to integrate over each one of them separately. So, for example, if we look at the tetrahedron from another angle, so here's X, Y, Z. Here's one side right here. Is this triangle. Okay. So what you would do is, so the parameterization of this surface is y is equal to 0, x is equal to u goes from 0 to 1, and then z, so you want z is going to be equal to 1 minus u, because what happens is, let's go to define the boundary. Okay. So I'm going to be our parameter v. V runs from 0 to 1 minus u. So, in this case, we don't have nice constant limits for everything because the region we're integrating over is a triangle. So when x is equal to 0 and u is equal to 0, then v is going to run from 0 to 1 and so forth. Now, the unit normal is going to point in this direction. We want outward, so it's pointing away from a tetrahedron. So in this case, the unit normal vector, n is going to be 0, minus 1, 0. So it's going to be pointing along the negative y-axis because it's outward. 0, 1, 0 would still be perpendicular to this side of a tetrahedron, but it's going to be pointing into it. We don't want that one. So what you can do is that the integral over this side of the tetrahedron, which I'll call S1, of whatever vector field you're given, over that surface, just that side of the tetrahedron, it's going to be the integral from 0 to 1 in U, from 0 to 1 minus U in V. Here we're going to have our vector field with x, y, and z plugged in. So it'll be U, 0, V. Dot product with
Isn't that a rat bike?
RU cross RV du dv. And this, when you work it out, from your parameterization, what we have is RU is 1, 0, 0. RV is 0, 0, 1. And RU cross RV is going to give you 1, 0, 0. So it's just going to pick off the x component. I'm sorry. 0, 1, 0 minus. So that's your normal vector, your outward normal vector. And in fact, if you compute the cross product, you'll find that's actually what you get is 0, minus 1, and 0. So it's just going to pick off a y component of this vector field, at least for this side. Now you'd have to repeat the process for the other three sides. So you'd have to, so for this side over here, the base, our outward unit normal would be 0, 0, minus 1. For this side, along here, this is your vector, minus 1, 0, 0. And then here we have a plane, x plus y plus z is equal to 1. Now the normal vector to that plane, we can read off the equation. So the normal vector is 1, 1, 1. Yeah, to normalize it. That's the unit normal there. And we know it's the right one because the it's got to be pointing up. The z component should be positive. And in this case it is. So, so what you really need to do is do what we did here. Parameterize all four sides individually. Compute your normal vector, make sure it has the right orientation. For that, you need an understanding of what you're integrating over, geometrically, visually. Then, you can make sure that your orientation is right, so that the sign of your integral will be right. All right, so...
What does that eventually give you?
What does...
Like after doing all the three sides, what can you give?
Oh, actually, you got to do all four sides.
Yeah, all four sides.
Yeah, so what that's going to give you is, in this case, it's going to be, so for instance, what do you mean, like how to interpret that, like physically or whatever? Say if F corresponds to velocity of a fluid, and I'm simplifying it of a uniform density, let's say, that it's going to be how much fluid per unit time is coming into the tetrahedron. Now, what that means is if the integral turns out to be negative, sorry, really it's coming out because it's outward unit normal. So if it's positive, then fluid really is coming out on a net basis. If it turns out to be negative, then the interpretation of that is fluid's actually going in. There's a net gain of fluid inside the tetrahedron. Yeah, there's quite a bit of what goes on in vector calculus, especially this chapter that relates to fluid dynamics, which is why it makes sense that one of the authors of the textbooks for this class also wrote a book on fluid dynamics. So it gives a lot of the physical interpretations we have of these things that are easier to understand. But there's also similar interpretations for involving electric fields, magnetic fields, which relate to Maxwell's equations and so forth. And I'm going to take a lecture and a half or so to say more about those things. All right, there are 5 minutes left. So